All right. Um, YouTube decided to change algorithms and how the thing works, so that took me a while to figure out. Anyways, so today we're going to talk about chapter 6, which is sampling distributions. And sampling distributions is it's an easy concept with a quasi easy execution, and it's actually much less complicated than one would think. So the idea behind it was, in chapter 5 we took one out of a population. We took one sample and said, hey, what's the probability we're gonna find this in here? And it worked both for proportions and means, right? We had some statistics on it. We could focus on the fact that we took a white die, or the fact that it has 5 dots. Either one, we could be like, hey, what's the probability we're gonna find this being, five dots, or 1 dot, or white and 1 dot. And that caused some problems, because if you just ask one person, your answer might not always be very precise about the population, right? It will be easier to ask 5, 10, 50 people, 100 people, right? This way you will build, right? If I take this, right, this might be a much better picture to describe this than just that, right? So this was this kind of concept that asking one, great; asking a lot, better, right? And so we were trying to talk. Now the reason why we even bother with this is because eventually we would like to start dealing with populations we don't know enough about, right? The whole concept of doing math on things that we know everything about seems to be um, counterintuitive, right? It's, why would I even study a population I know everything about already? So the reason why we started taking samples, or starting asking about individuals out of a whole group, was, hey, is there something there that is worthwhile investing, right? Investigating. Is there something there, right? And this whole concept of asking bigger groups just makes sense. Plus, if I was going to judge you and your whole family based on talking to one member of your family, how secure would you be that I'm not going to call up your crazy auntie, or your crazy uncle, or your, I don't know, 5-year-old nephew who doesn't like eating vegetables, right? There's this whole concept. On the other hand, if I spoke to most of your family, or a big chunk of your family, right, the picture of what your family is like really would be much better, right? I do have one of those crazy uncles, and honestly, if you talk to him and you're trying to judge me by it, yeah, but I would prefer you didn't, right? There's so many cooler people to talk to, like my grandma. You talk to her and you judge me based on how awesome she is. I'm all for it. That crazy uncle, I prefer you not, right? He is kind of certifiably crazy. So this is what we're going to do in chapter 6. Now, because of this, I am going to be swapping between this view and the textbook, and back and forth, because there's a couple things there that seems to be presented in a way which I cannot do better. But I'm going to try to work through it. Now, again, there's some scary formulas in there. There's some things that we are introducing. One of those scary things is this, and the other one is this. Now, I know, very scary. Ooh. All right, let's break this down. What is this? Well, that's a sample mean, right? That's a sample mean. And what is this? Well, we cannot use mean, because mean is like the Mean Girls all over again. But what can we do? Well, we could say an average, right? So this is an average. Well, it's an average of what? Well, of sample means. So this is an average of sample means. That is a standard deviation of sample means. That's all there is. Sample means, standard deviation. Right? There is no hidden meaning, no hidden agenda here. Just an average of sample means. So we take a sample. There's a sample. For those of you who don't see, that's 6 and 6. So right, the average here is 6, and there's your one mean of a sample, and then we can do another sample and another sample and another sample. Now, because we are taking samples of the population, so if this is a population, if we take a sample of this population, that's one of the possible means, right? Because here, when we are talking about sample means, we are talking about all the possible means, right? The possible sample. So that's one possible sample. There's another, and there's another, and there's another, and there's another. All those, right, are, but this die could also go with this one. That's a possible sample, and that's a possible sample, and those two are possible samples. So you see how this kind of balloons very quickly, right? If we looked at just smaller amount, so let's get 3 different colors, right? So how many samples can I do? Well, I could do this as a sample, right? I could do this as a sample. I could do these two as a sample, right? So these 3 have 3 samples. Now I add one more. These 2 could be a sample. These 2 could be a sample. These 2 could be a sample. These 2 could be a sample, right? And these 2 could be a sample. Right? There's a lot more samples than there is individuals once we get past a certain point. Now, why would we want to take all those sample means, all of them, and then take an average of them? It seems counterproductive. But this is exactly what we're going to do in example 1, so just bear with me. So in example 1, let me scroll here. In example 1 says we have 152, 156, 160, and 164. Find all possible random samples with replacement of size 2 and compute the sample mean for each one. Okay, well, that sounds... I'm just going to go right ahead and... Sorry, apparently lots of trucks today. Alright, so let's see. I could go 152 with itself. 152. Then I could go 152, 156. I could go 152, 160, 152, and 164. Then I could go 156, 152, 156, 156, and so on and so forth. So if you take a look at here, there's the table. So this is how they produce the table. They just made combination of each one of them. And I'm going to use the table for now because it's easier for us to see it. Right, so while we're looking at this, let's go back to paper. 156, 160, 156, 164, 160, 152, 160, 156, 160, 160, 160, 164, 164, 152, 164, 156, 164, 160, and 164, 164. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so there's my samples. Let's calculate the average of those. And in average, I'm going to do red. And this is 152, 154, plus 4 minus 4, 156. And this is 158. Then this will be 154, 156, 158, 160, and this would be 156. These two would give an average of 158, 160, 162, and this would be 158, 160, 162, and 164. All right, let's count them up. Let's see. How do we do it? Well, let's do it this way. Let's put an X bar here. And let's see what we have. We have 152 here. Do we have any more 152s? No, that's one. So I'm going to put frequency here. 1. 154. 1, 2. That's 154 is only 2 of them. 156. 1, 2, 3. So 156 is 3. 158. 1, 2, 3, 4. So 158 is 4. 160. 1, 2, 3. 160 is 3. 162 is 1, 2. And 164 is 1. 1, 3, 6, 10, 13, 15, 16. Yes, 16, which accounts for this. Alright, so now that we have this, we can find the probability. Right? And the probability is what? Well, in our case, that's going to be F divided by N. Right? Because this is our total number of samples. So this is 1 out of 16, 1 out of 8, 3 out of 16, 1 out of 4, 3 out of 16, 1 out of 8, and 1 out of 16. Cool. All right, so this is done. So this was all the possible things. Now we needed to find the mean and the standard deviation. Well, the mean. So the mean of all those things, right? The mean of those things is the sum of right, we remember this formula from a previous chapter. Just this time around we have bars. But so what? It's just the same thing. So it's this times that plus this times that plus this times that plus that and so forth. Right? We just have to multiply those two together. Well, let's see. So this is equal 152 divided by 16, right? These two, plus 154 divided by 8 plus 3 times 156 divided by 16 plus 158 divided by 4 plus 160 times 3 divided by 16 plus 162 divided by 8 plus 164 divided by 16. Alright, so let's see. 152 divided by 16 plus 154 divided by 8 plus 3 times 156 divided by 16 plus 158 divided by 4. By the way, my dyslexia is loving it. 160 times 3 divided by 16 plus 162 divided by 8 plus 164 divided by 16. And behold, 158. So that's the average of sample means. The average of sample means is this. But if we looked at this and we just cleared up 152 plus 156 plus 160 plus 164 divided by 4, right? Added those up. So sum of the average of this anybody see similarities here? Right? This concept comes around and you're like, oh, why am I doing this if I could have done this? And we're going to get to that in a second. But here's the cool part. This is our average of our population, right? This is our population, this is our average. It's 158. Which means what? Which means that if we were to look at this, those are averages of the samples. Would this sample reflect this population pretty well? 6 away, it's not very good. Better, right? This is better estimate. This is a pretty good estimate. If I said 158, you got me 156. That's pretty close. 158 is on the money. 160, it's not bad, right? It's 2 points away. It's not bad. That's 4 points away. I'm not impressed. And that's 6 points away. That's not very good. But look at the frequencies. We're mostly going to, if we had to pick one, we're going to end up over here, right? So this is kind of this concept of, hey, all those samples are estimating this population, right? We are estimating this population. And the bigger the sample we take, the more we estimate the population. And that's going to come in a second. All right, we need to calculate the standard deviation. Because we love standard deviation. All right, standard deviation. What's the formula for standard deviation? The standard deviation formula looks something like this. So something like that. Well, so let's 56, 158, 160, 162, 164. So I got myself the column x. So I'm going to get myself a column x squared or x bar squared and 152 squared. It's 23104. 154 squared. 23716. 156 squared. 24336. 158 squared. 24964. 160 squared. 25600. 162 squared. 26244 and 164 squared. 26896. And then probabilities is 1/16, 2/16, 3/16, 4/16, 3/16, 2/16, and 1/16. Alright, so let's multiply those out. This times this. So this is x bar squared times p of x bar. Now I know one could go into a cool looking thing and something like that, for example, and and just go calculate, and there's the average, and there's the standard deviation of just those four numbers. And I could have done that, but what fun would that be if we didn't do it by hand, right? And the reason why I'm doing it by hand, so you don't have to, or if you want to follow with me, because once we do it once by hand, we understand the process, and then using a calculator is much more clear. So I'm doing it by hand. So 23104 divided by 16. 1444 23716 times 2 divided by 16. It's 2964.5. 24336 times 3 divided by 16 is 4563. 24964 times 4 divided by 16, 6241. 25600 times 3 divided by 16 is 4800. 26244 times 2 divided by 16, 3280.5. By the way, do you guys know what the leading cause of bad grades in statistics is? Sloppy penmanship. If you write things crooked and then you try to squeeze too much. The reason why I use those thick markers is not only so you can see it, but so it forces me try not to squeeze things too small and together. Anyways, so let's sum this up. Sum of x bar squared times p of x bar. Alright, so sum those things up. 1444 plus 2964.5 plus 4563 plus 6241 plus 4800 plus 3280.5 plus 1681. And I got that the sum equals 24974. And so is 24974. Ooh, I made a mistake. There should be a square here. Alright, well, glad I saved it. Minus 158 squared. How much is 158 squared? 158 squared. Alright, so this is 24974 minus 24964. Let's see if I made a mistake. 24974 minus 24964. I got square root of 10. All right, well, this is what I got. So here's my mean, here's my standard deviation. All right, well, if we were to calculate this, let's use those numbers. 152, 156, 160, and 164. We know that the mean of that is 158, and we also know that the standard deviation for that is that. And I'll let you sort this out, and either you can do it by hand or you could, use a website, and there it is. There's my square root of 20. So, again, it's up to you. I'm not judging. But, same, different. And that is important. Because what we realize is that if we have just our population, the distribution of values is slightly different than the distribution of the sample means of it. And the difference of that is the following. We realize that this, regardless if we take an average of those samples or if the population, we are getting the same thing. But if we are getting this, it's not equal to this, right? The standard deviation seems to be much smaller here, which means what? What does mean standard deviation is much smaller? So let's take a look at it. We had 4 values, right? So we had 4 values, and we had the same frequency. Let's build it this way. And we had the same frequency for every single value. So let's call it. I don't have enough dice. Let's call it this way. Right? We had. Oh, actually, even better. Let's do it this way. I'm going to toss this aside. So we had same frequency for 152, same frequency for 156, same frequency for. And I apologize, guys, for different colored dice, but that's what I have. Actually, not. No, better. Better. This is the part of statistics I absolutely love, the visuals. You don't get enough of them in teaching. So here you go. Each one of those white stones represent a frequency. So there's our frequencies for 52, 56, 60, and 64. Some space. Actually not. Let's make it even better. Let's make it this. 152, 156, 160, and 164. And there's the 4 frequencies. And on this side we're going to have. No, that's not going to be big enough. Go. There's my distribution, and on this side we're going to have 152, 154, 156, 158, 160, 162, and 164. And let's look at the frequencies for that. We had one here, one here, two here, two here, three over here, three over here, and then four over here. It's not very neat, but alright. Now, again, I don't mean that there were four of each, there were one of each, but they were just equal. And last time I checked, 4 1s and 4 4s are the exact same thing when it comes to frequency. So this is the kind of setup. So we went from this to that. Now where's the mean? The mean was right here, right? At 158. So somewhere between those two, there was the mean of 158, right? This is what we calculated it was. And same thing here, the mean was somewhere here, right? 158. So what does this mean? Well, it means that this shrinking of the standard deviation gives us a very nice kind of a shape where most of the samples, right? Most of the samples, and again, if we remember doing this, right? Most of the samples are focusing on the mean, where each one of those can miss. But 156 is a pretty good estimate for the mean, so is 160. But neither of them is actually very precise, and this is much better, right? And as we take more and more samples, right, the next one, if we took, and I'm guessing here, if we took more samples, it would maybe look like this. Maybe, let's put it, look, how low can you see this? Okay. So maybe next one, right, would start to look like this if our samples got even bigger. And all of those starting to have this kind of shape, and we know what this shape is, right? We know what this shape looks like. That's a standard normal distribution, right? And this is the really cool part, is if you take a single sample out of here, you can get close to this, but you can get also very far away. But if you have a actual sample that is bigger than 1, you start getting see this pattern, right? Now, the average for all 3 of those distributions is the same. It's 158. However, the standard deviation is largest here, smallest here, right? And eventually what happens? Well, eventually if you take a sample that is size 4 out of this, if you take a sample size 4, what you're going to get is you're going to get a distribution that looks like this. And I apologize, this is a spur of a moment greatness. It's going to look like this. Right? Why? Because if you take a sample of 4, right, you're taking a sample of the population, and that's exactly this is 1 point kind of setup, right? So this is really, really cool, and again, it might feel a little foreign, but this is this example 1, and the reason why we went through all these calculations is just to do this, is to prove that the average, right, the center of mass, if you think about this as a visual spatial thing, the center of mass for both of them is the same thing. It's right here in the middle. But how it aggregates around that center is very different. Here it's, half and half, right? But the outside is heavier here and lighter here because it's all getting together. And the bigger sample you get, the more aggregated it is towards the center. Excuse me. Another way to think about it is if you think about your friends and you have some really light friends weight-wise and some really heavy friends weight-wise, right? Maybe a local sumo fighter is one of your buddies. What are the chances that if I randomly take your phone book and pick out 10 of your friends, I'm gonna luckily pick the 10 lightest friends? It's small, right? Or the 10 heaviest friends. Very small. Usually I'm gonna pick somebody who's light, somebody who's heavy, and I'm gonna average about here, right? I'm gonna pick 5 little lighter, 5 little heavier, right? Maybe a little bit off. Maybe I'll pick 7 heavier, 3 lighter, but I'm going to aggregate towards the middle. And the more of those samples I take, or the bigger the sample I take, the more I'm going to get towards the middle. And that's the beauty and importance of the first, 2 pages of chapter 6. It's absolutely mind-blowing. Now, let's get to example 2 and keep working. But, guys, really cool, and, well, if you're getting that, the next chapter is going to be a breeze too. All right, so actually let's use this poor piece of paper first, so we don't waste. So example 2. Right. Example 2. The mean is 13525. And the standard deviation is 4180, and the sample mean population standard deviation sample size. And we are asking for, well, we know what this is. Well, this is exactly this, which means this is still staying. Now this, on the other hand, is tighter than the population one. Well, so this is 4180 divided by square root of 100. Square root of 100 is 10, so this comes out to be 418. Then that's it. This is just kind of a, hey, let's apply it. Now, why are we doing this? Well, because eventually we want to be able to convincingly say that if we take a large sample from a population, right, from a sampling, we want to be able to say that theoretically sampling distribution will have this, right, and our sample fits into this, because the bigger our sample is, the more likely it is ending up in the middle. It's very unlikely to take a sample which only has the smallest or the largest pieces in it. It's more likely that we're going to get combination of thereabout, right? If you think about your, say your population looking like this, if I start taking a sample, I take a sample, where's my red pen? If I take a sample of 1, I can either get one of those or one of those. Either somebody who's really tall and somebody who's really short. But the more people I pick at random, right, I'm going to eventually pick some of the tall ones and some of the short ones, some of the short ones, some of the tall ones. And what is going to happen is that once your sample is sufficiently big, the chances of picking only the tall ones is really, really small, or only the short ones is really small. Most likely, I am going to end up somewhere in the middle. And this is all it's saying, is that I went from this standard deviation, for example, in this setup, this, to something really small for this. And the bigger the sample is, right, the bigger this number is, the smaller this fraction becomes, which means the smaller this red line, standard deviation for the red line comes, so its whole thing goes tighter. So that's that. Oh, look at that, we already did that. So 98 we're good. But here's the good, really cool description here. And I'm going to pop it on the screen. This is on page 198. Right? This kind of concept of different samples, right? And again, if you look at it, the more samples you take, right, the more spread around it becomes. Now, mind you that when it comes to sample 20, it actually requires 2 lines because this thing becomes so wide. And again, all of it seems to be aggregating in the middle. Right, so this is, and here's the, right, it went from a uniform distribution, which is the orange one on the left, which is, you know, both chances are equal, to starting to spread around. And eventually when it got to size 20, that looks normal. That looks almost normal, right? So this whole concept of expanding our samples is this. Now, why we do it? Well, because we want to know that our samples that we're taking are actually reliable. The fact that we take one individual piece of data and we can do something with it is great. But if we take a large set of those individual pieces of data and do something with that, now we're talking, right? It's the whole concept of what happens if you get unlucky once. Well, if you get enough tries in the pool, the chances of this showing you actual chances of winning or losing, for example, are much better. All right, so that's that. Let's see what we have further down. Central limit theorem. Yes, central limit theorem. This is another one of those great things. Central limit theorem says the following. Says if you have a large sample, and again, depending on which textbook, which professor you ask, which source you look, large sample means 30 and above 30, above 25. Some professors even said above 50 or above 100. Depending on who you ask. If you have a large sample, in our case, let's go 30 or more, then this concept, this thing, applies. So you have a large sample, this applies, right? The mean of the population is the mean or the average of sample means, and the population standard deviation divided by the sample size gives you the standard deviation of the sample means. But what does it mean? Well, it means that regardless of where you started, right, what's your population looks like, eventually we're going to start seeing a normal distribution in each case, 30 and above. So it doesn't matter if we were this kind of uniform distribution or something that has lumpy or weighted on one side, right? Because this means what? This means that starting from here, most things are on this side, and there's a couple tall ones. But if you start averaging, this thing is going to start shifting, eventually ending up looking like this, right? It's this beautiful concept of things just working. All right, so this is the basic idea. So I hope this fits. All right, let's keep going, because I feel like I've been talking for a while and we are not moving forward. Oh, look at that, we are 45 minutes in and I'm only arriving at example 3. God, I must love this subject. I do. Almost as much as you hate it. And the more you hate it, the more I love it. Well, that would be cruel, but it's true. True story. Statistics. All right. Example 3. Let x be dum dum dum. So we have sample size of 50, and we have a population mean of 112, and we have a population standard deviation of 40. So this is example 3, and it says find the mean and standard deviation for this. So we need to part A. This is example 3 in chapter 6. Good morning, how are you? You're doing great. Mean, so we need to mean of this, well, bigger than 30, and I'm done. It's bigger than 30 when, so this comes true holding this. Standard deviation of this, again, bigger than 30, which means that this is not 50. 40 divided by square root of 50. Where's my calculator? Kingdom for a calculator. Alright, so this is 40 divided by square root of 50. 5.657. Alright, so this is A. B. B is asking find the probability that X means assumes the value. So probability that that. Now it doesn't matter if I'm doing bigger and equal or just bigger. No, again, because we are talking about single pieces, and single pieces don't matter. It's a single grain of rice. We had this conversation before, so I could have written this, but I could have just as well written this. So that's done. All right, so there's a couple ways to do it. One way is we can think about this as a z problem, right? We used to have z equal to x minus mu divided by sigma, right? And now we just have z x bar minus mu of x bar divided by sigma of x bar. And there is this, right? We could also look at this as saying one more thing, and this is how you will see me do it on the videos from previous years, is where I just took this and I said that z equals to x bar minus mu, because this is actually mu, right? For large sample, this is actually mu, divided by sigma divided by square root of n, which is this, right? And I rewrote it as, because if you divide by a fraction, you can multiply by its inverse. So all three of those are the same thing. In my old lectures, I used to use this and this. Why? Because I just didn't want to do this calculation every time and then use this decimal point, because it eventually you have to round it. So if you keep on adding this in here, you hinder the writing. When if you plug in this whole thing in the calculator, this rounding is internal and it doesn't skew your results. So either one works. So let's see. I'm just going to put this over here and let's go. I'm going to use let's see, the problem in the book is solved using this method, so I'm going to solve using this method just because confusion. So what I'm looking for is I'm looking for P110 smaller than x bar smaller than 114, which means I'm going to find the z-scores for both of those. So the z-score for that is and I'm going to use this formula, which is again the same one as this and same one as this. So in our case, that's 110 minus 112 divided by 40 times square root of 50. And I come up with, now here's the trick to typing this in. You go 110 minus 112, enter, divided by 40, enter, and then times square root of 50. And that comes out to be negative 0.354. Okay. And I'm going to solve this one using this formula. So and this is 114 minus 112 divided by 5.657. And again, 114 minus 112 divided by 5.657. And I get 0.354. So this is really negative 0.35, right? This number smaller than this, no, smaller than z, because we switched it to a standard normal, smaller than 3.5. This. I'm going to get my trusty table, and if you don't know how to use your trusty table, look at the previous video. And what I'm going to do, I'm going to say, and this is 0.35, this is negative 0.35, and I'm looking for this, so I'm going to look up this probability first, and this probability equals 0.35. (6.368). And I'm going to look up this probability, and this probability is going to equal negative 3.5, 3.632. So this whole thing is going to equal to 0.6368 minus 0.3632. So that comes out to be what? 6.372. So that's how I solve part B. And then let's look at part. Is it me or just the light? No, I'm gonna have to put a second light here. Alright, and then we're gonna solve the second one. And see probability that X bar is greater than 113. Okay, well, let's find the z-score for that. So this is, let's use this formula maybe. (113 minus 112 divided by 5.657). So what we're looking is for probability of z being greater. And again, since our table only gives us 2 decimal places for the z, I'm going to round this up one more, 0.18. And this is greater than So I'm looking for this 0.18, and the probability for that equals to 1 minus this. So 1 minus this. So probability for 0.18. Oh, I love those small numbers. 5714. So the probability for z being greater than 0.18 equals to 6, 8, 2, 4. So probability for Alright, so that's done. Let's keep going. Alright, let's go example 4. To the side. Example 4. And example 4 says we have some mean at 2.61. We have a standard deviation at 0.5, and we have a sample size of 100, and we are looking for probability that the sample mean is going to be between Alright, well, any way to solve it is good, since we could solve it any way we can. You can go this route. You can go with the route saying, hey, this equals to this equals to, and this equals to because this is sigma divided by square root of n, which comes out to be 0. This is 10, so this is 0.005. You could do this route, or you could just do this. And in that case, our first one will be 2.51 minus 2.61 divided by 0.5 times square root of 100 is just 10. -2. And then the second z-score again, all of those same. It's question of, are you substituting things in or are you not? And either way is fine. I like this one because that's the way I've been taught, but recently I found that this makes more sense because this formula is really scary. It's a double fraction and people seem to hate double fractions. So I have a feeling that this is going to be also, it's going to be just 2. So what we're looking for is for probability that -2 is smaller than z smaller than 2. So why am I drawing the goddamn picture even though the examples don't in the book don't do pictures? Because pictures are good for you. The more pictures, the better. You don't draw pictures, you might make a mistake. And considering that this is a 6-week course, making mistakes is just bad juju. Alright, so let's find the probability for 2. Probability for 2 and 0.9772. Probability for negative 2, 0.0228. So probability for damn, it's a loud car. I'm sorry guys. It's downside of working from home and not being able to afford an office with an AC. This equals to 0.9772 minus 0.0228. So this comes out to be 44590. And there's your answer. Pretty cool. Right? Again, why are we doing this? Is because we're starting to talk about, hey, is this sample fitting in? Because the more we know about what the sample is doing, the better we can say, hey, right? If we have a confidence in the fact that if we take a large sample, this sample is going to be matching the population pretty well, right? Then we can do certain things like in about 3 months we're going to be voting, right? I hope you guys vote. Exit polls are done this way, right? How do we know who's winning, who's losing? Well, we do exit polls. Exit polls are samples that tell us what the voting overall is being done. And the rule of thumb is that if there's a discrepancy, or at least United Nations has this idea that if there's a discrepancy between this number and this number bigger than 1%, right? Then there is usually concern about problems with the whole event, either because the exit polls were done poorly, or because people were lying about their voting choices because there were people present, or because there was certain votes weren't counted, or because there was meddling. In Serbia, I think there was a vote, and the difference between exit polls and the actual results was off by 1.5%, and there was an investigation into election meddling. Funny story. In New York, back in 2016, when there were primaries for Democratic candidate, Bernie and Hillary were going against each other, and the exit polls were suggesting Bernie winning, or at least being very close. The difference between exit polls and the actual results were off by 12.5%. 12.5%. We considered 1%, bigger than 1%, election fraud. I'm not saying there was election fraud. I'm just saying that something went astray, right? Again, you could have just taken a really bad sample. If you take a really bad sample, it's not going to match the population, right? But I'm saying that this starts giving you a power of deduction. Like if you are telling me that you have the smartest students in your class out of the whole university, great. If I randomly pick 10 of your students, or 20 or 30 of your students, and I start getting grades that aren't spectacular, well, either my sample was really badly picked, or I picked from the wrong population, or whatever, or I asked the wrong questions, or your statement is wrong, right? So this is starting to give us a lot of power to do certain really cool things in the future. And that's chapter 8, 7 and 8 mostly. Chapter 8 we're just going to cover. There's not going to be a homework for chapter 8 to be done because the time crunch, but just mind you that there's a lot more cool things happening. So I hope you guys stick around for statistics a bit longer than what this class is entailing. All right, let's look at next next thing. So this was example 4. Now page 102, I apologize, page 102 looks really funky, and the reason why it looks funky is because this is important, and I wanted to keep that on a single page. This. And this is what I was saying, that if we start pulling bigger and bigger samples, we're going to get closer and closer to the truth, right? Eventually we take a sample the size of the population and we arrive at the exact spot. But the closer we are, the more likely we are going to end up in the middle, and the less likely we are, because the standard deviation is getting smaller, the less likely we are to get results that are very much off. And again, when we do polling for things, if you look at the fine print, and it has to be in the fine print, either on the website or underneath the actual poll numbers, and on TV the fine print usually looks like grains of sand, but there is a fine print. They have to tell you how big your sample is, and if you look at closely, some of the samples are huge. They're like 40,000, 20,000 people got asked. If there's a sample size of 10, that's bullshit. Just don't even bother with it. But if there's a sample size of like 4,000, okay, that might mean something. Now again, question of how you sample. Hillary Clinton thought she's going to win against Donald Trump, but again, their sampling problem was the fact that they didn't sample Latinx women, they didn't sample black women in their samples, or not enough. So when those populations started, those parts of the population started voting, you ran into a problem of the polls not matching the final results. Again, there is a sampling error. If you ignore certain groups and they actually do something that you weren't expecting or weren't prepared for, well, that's your problem. And so that was a big issue. Anyways, so here, if you overlay them, all three of them, this is what they look like, right? The whole thing gets tighter and tighter and tighter and tighter together, with the standard deviation being smaller and smaller and smaller. The average, right, or the center of the mass, the expected value, doesn't change. What changes is how widely distributed this thing gets. All right, let's look at example 5. Example 5, we have a prototype, we have some numbers, and we do the calculation. Well, I promised to do every single one, so let's do every single one, although this one honestly feels like all the previous ones. I'm not complaining. Alright, so we have a mean of population mean is 38.5k, and standard deviation is 2.5k. Can find I'm sorry, I lost track. Find the probability that a sample will be less than, assume this. Okay, so we have normal distribution. Oh, here it is. 5 such tires are tested, so n equals to 5, and it's normally distributed. Now the reason why they say it has to be normally distributed is because our sample is small. If our sample is small and it's not normally distributed, we cannot work with this, right? This whole idea comes that if the sample is large, it's normal. The sampling distribution is going to be normally distributed. But if the sample is small, we might not necessarily get that chance. So if you look up page right, if you look at this page, which is 100, if you look right here in the middle, those two still don't look normal. Like this one that doesn't look normal, right? So there is not much we can do with these and whatnot. So we either need a large sample, or we need this to look normal to begin with, which we saw on right here, right? If it was looking normal from the get-go, it's just going to look more and more normal as we take the sample, or not more normal, but it's going to look more squished, but still normal. All right, so example 5 was this. So the reason why I said k is because I just don't want to write all the zeros. So let's look at this, and we say probability that x bar is going to be smaller than 36k. That. Alright, so let's turn this into a z-score. So z equals to x bar minus mu divided by sigma times square root of n. Again, we could just find this using that and apply it, but old habits die hard. So this is 36k minus 38.5k divided by 2.5k times square root of 5. Well, k's are going to cancel out, so what we're going to be left with is 36 minus 38.5. 36 minus 38.5 divided by 2.5 minus 1 times square root of 5. So what we're looking for is that. So we're looking for this, and this equals negative 2.24. Negative 2.24. I'm getting 1.25. 0.0125. And what does this mean? Well, it means that the probability that we take a sample of 5 tires, right? Only 1.25% of the time, right? Or 1.25 probability of the sample showing up with 5 tires will have an average below 36,000 miles. Right? This idea is that now we know that even if we take a sample of 5 and we have 1, 2, 3 really good tires, one of them is going to be a dud. It's going to bring the average, but that's very unlikely that's happening. Right, because the population average is this, we would expect all the samples to be around the population, right? If this right here is the average, we expect most of the samples to come from this area, not from this ends, right? So this is kind of cool. And again, there's calculators for this online if you don't want to do it by hand. Alright, so that was, oh, hang on. So this is 5. Pause if you want. Alright, let's look at 6. Alright, let's see. What do we have there? Battery manufacturer has a mean of 50 months. So this is example 6. Battery manufacturer has a mean of 50 months. Good. With a standard deviation of 6. So far we're on the money. Suppose that the battery right, assume that the manufacturer's claims are true. Find the probability that randomly selected battery of this type will last 48 months. So A is probability that a randomly selected battery, so X smaller than 48, single battery, right? This is important. And so we find our Z is X minus mu divided by sigma. Why? Well, because this is a single battery. Single battery. This is important. So in our case, that's 48 minus 50 divided by 6. So that comes out to be negative 1/3. Let's see. 48 minus 50 divided by 6. Yep. Negative 0.33. And so we're looking for smaller. So we're looking for this. And what's this probability? Well, if we look at the table, it's negative 33. It's 3707. Right? So that's our answer. So there's 37% that we're going to pick a battery that's going to survive less than 48 months. Cool. Now part B, by the way, this is a really cool example, like really cool. This is, I think, the best illustration for this, is sample mean and same mean number, and we're going to go sample size. So get 36 of those batteries, and we're asking for okay, well, we're doing the same thing. Z x bar minus mu divided by mu to x bar minus sigma x bar. Let's do it this way. Sample bigger than 30, so this is equal to that, and standard deviation of sample means is this divided by the square root of this, so that's 6 divided by square root of 36, which makes this equal to 1. So our Z becomes 48 minus 50 divided by 1. So that becomes minus 2. We're looking for this. And then minus 2, we just did that. It's 0.0228. So the probability of finding an average, so to find randomly selecting 36 batteries whose average is below 48 months is 2.28%. This is 37.07%. So picking one out of 3, but picking 48 and all of them on average being below, very small, right? It's this concept that the bigger sample you take, the less likely you are of just getting bad choices, right? If you have a platter of 10,000 pieces of sushi, right, or pieces of sashimi, and you pick one, and that not being perfect, there is a chance for it, right? It depends on the chef, but there's a chance for it. But you eating half of it, and on average all of it sucks, not really likely, right? So this is a really cool example because it illustrates the difference between this, right? Suddenly we go from z-score close to 0 to a z-score that is far from 0. Right? The jump from 37 to 2% is very substantial, and all it took is just checking 36 batteries. So this idea of checking samples, right, and constantly testing is worth it, right? Same thing could be that you test one and you got something that is spectacular, and it's like, oh, my whole production is spectacular. No, keep testing, because maybe you just got lucky. So this is really cool. Example 6 is, I highly recommend everybody just wrap their head around example 6. All right, let's see that. Sample proportions. All right, so for sample proportions, we can have the average of sample proportions, and that's just the population proportion, and we can have the standard deviation of sample proportions, and that's PQ divided by N. Why is it PQ divided by N? Anybody remember? We said that the standard deviation for binomial distributions was what? Square root of NPQ. So if we take this and we just apply this, right? That doesn't work. Right? It's starting. So question is, why is there an N here? Right? Because if we try to do this by hand, we suddenly run into a problem of like, what's going on? The reason why this N is here is because our standard deviation needs to shrink as we increase. Standard deviation needs to shrink as we increase the sample size. So this N needs to be here. So if you start starting from scratch working on it, be very careful. This is important, right? This N right here is very important. So, all right, so those are the two formulas, and we know what P equals 1 minus Q and Q equals 1 minus P, so that's that. Then there's a description of what P is, and I think that's relatively straightforward. Now, sampling distributions and sample problems. Now here we need to consider the following: is how do we know sample is big enough? If we are talking about a sampling distribution for a mean, we talk about how big the sample is, and we have a very well defined number, and in this case is 30 or above. But when we talk about proportions, we run into this problem of, well, what happens if the proportions look like that? What happens if the proportions look like that? Is this enough of a sample size, or do we need to go, bigger to have a chance of grabbing the single piece, right? This is this kind of larger conversation, right? What happens if our proportions look like this? Well, then our sample needs to be a lot smaller to actually have a chance of grabbing both the white and black stones, right? But if our thing looks like this, well, then in that case we really need to pick a large sample to make sure that the black stones have a chance of being caught. Because if you just take couple and say, hey, well, this sample is all white, it's not all white. There's two black stones here, right? So we need to grab a large sample and be like, okay, there's some black stones in here, so it's not all white. It's predominantly white, but not all white. So that's this kind of idea. And the way we check this is we say, hey, if we have the sample range within this, if we take this and we have the sample range and this whole thing ends up being within somewhere between 0 and 1, then our sample is good enough. Now, why do we bother with this? Well, we bother with this because if our sample is really small, then our standard deviations is very large, right? If our sample is very small, then our standard deviation is very large, which means that the whole thing balloons. And here's an example of what it looks like when it balloons, right? This whole thing, this left graph, right? Those things are really shifting to the left of 0. So this is just very wide. But if we take a large sample, we have a lot more distinction, and all of it gets squeezed in. And because it gets squeezed in, the free standard deviations away, which is the 99.7% of the data, ends up being relatively close to the middle. And so this is how you check. We just check this. Now, we could run into a problem of saying, hey, well, how do we do this? Well, let's look at example number 7, which is actually the description of it. I produce so much paper. All right, so example 7, we say that the certain proportion is population proportion is at 0.38, favor of something, 900 randomly selected, so n is 900, selected if they vote bond. Okay. A. Verify that sample proportion p hat compared to the sample size of 900 meets the conditions of sampling distributed by approximately normal. Alright. So for that we're going to need a couple things. We're going to need p, we have p, we're going to need q, and q is 1 minus p, so in our case q is 260, so we have q, and we're going to need this, and that was defined as pq divided by n. Now what's pq divided by n? Well, the 0.38 times 0.62 divided by 900, and all of it in the square root. That comes out to be 0.38 times 0.62 divided by 900, and then square root of the whole thing. And I got 0.0162. Alright, so now next thing we need to do is that, so times 3, and that comes out to be 0.0485. Alright, now this has 2 decimal places, we have 3, so I'm just going to round this I'm going to round this to 0.049. Alright, and now we need to find p minus 3 sigma p hat, p plus 3 sigma p hat. I need to find this. Well, let's see. This is 0.38 minus 0.049, and this is 0.38 plus 0.049. So this becomes 0.331, and this becomes 0.429. Well, is it in this? Yes. Sample big enough to be normal. Right, so this is how we check that this sample causes this distribution to the sampling distribution to look about normal, approximately normal, right, or to be considered normal. So this is how we check A. And now B, find the probability the sample proportion computed from the sample of 900 will be within 5% points of the population proportion. What does it mean to be within 5%? Well, 5% means 0.05. Within means that, right, this is, oh, sorry, minus, and this is, that's within 5%, right? Smaller than, this is in this range, right? P minus 5% and P plus 5% is this. Well, what was our P? Well, P was this. So what was that? Well, that's P minus, so 0.38 minus 5% is 0.33, and plus 5%, this is 0.43. So what we're looking for is probability that 0.33 is smaller than P, smaller than 0.43. What? What? Where's my X bars? Where's my mu's? Like, oh my God! You know, this is an hour and a half into a video, and oh my God, I don't know what I'm doing. So, where are we going with that? Well, normal, Z, right? So let's see. How about we have P hat of some sort, maybe. So maybe we do this, right? Something like that. Well, this doesn't make sense. This is standard deviation, which we usually talk about means, so this doesn't work. Alright, so how about we do, remember that X bar thing we did? We did this X bar minus mu X bar divided by sigma X bar. Remember this? Alright, so P hat minus mu P hat divided by sigma P hat. Right? Just instead of X bar, I'm using P hat. Both of them are normal, why not, right? So what do I get? Well, if I do this for the first one, what do I get? Well, this is our sample, so this minus mu of P hat. Well, mu of P hat is the same as P hat, right? We talked about it. Sorry, mu of P hat is exactly the same as P. So we talked about this, right? This idea that mu p hat is exactly p, right? Mu of x bar was mu, but right? So this is 0.38 divided by this. And what is that? Well, we have this right here. And so our z for the first one comes out to be 0.33 minus 0.38 divided by 0.0162. Let's calculate the z for the other one, for the second one, for this one. There's a 0. So I have a 1 z-score, 2 z-scores. That's negative 3.09. And so let's look at this probability for that. 3.09. And probably for that, because we're looking for this area, right? Negative 3.09. That. And so our probability that right within 3 standard deviations, 99.7. So this is about right. Again, how do we do it? We do it exactly the same way. Well, first of all, we need to check if we can approximate it with normal, and this method right here to check if this is within 1, between 0 and 1 is a way. Once we have this, we know that this, and we know this. We know those two, right? That's the calculation for this one. We know those two, which means that we can use this z, p hat minus mu p hat divided by sigma p hat, and we just do it this way. And once we have a z-scores, it's just picture table. So that's example 7. And example 8, which is the last one. Example 8 claims 90% of the orders are shipped within 12 hours of being received. A customer group placed. Okay, so this is example 8. We have 121 orders of different sizes, different days. 102 shipped on time within the 12 hours. Compute sample proportion of items shipped within 12 hours. So A is this. I'm going to call X. I'm going to call things that are shipped on time. So proportion of this. So this is this. So this is 102 divided by 121. So this is 8 for 0.84 3, 0. Alright, so we have proportion. B, confirm that the sample is large enough. Use P of 90. Corresponding assumption of the. Okay, so B. P equals to 90. And we need to check if this. So if P is equal to 90, Q equals to 1 minus P. So equals to P cannot be 90. P can be 90%. So this is 0.1. Right. So if P equals to 90%, then P equals to 0.9. Thus Q equal to 0.1. P has to be between 0 and 1. Proportion cannot be smaller than 0 and bigger than 1. So if you see 90, that should probably draw your attention. Oh yeah, it even says 90. I just read it's 90%. No, I'm special. So we're not worried about this, not worried about this. Okay. This and N is 121, and we need to satisfy a couple of things. Well, first thing we need to do is this. Well, they told us to use 90, so we're going to use 90. So this is, sorry, this is, the formula is PQ divided by N square root, right? So this is what we're looking for. And 121. So this is what we're looking at. So .273. There's a 0. 0.027. All right, so we have that, and now we need to check if we can use normal. Well, to check if we can use normal, we have to go P minus 3 sigma P hat P plus 3 sigma P hat. So in our case, that's let's do 3 sigma P hat equals 3 times 0.0273, and that equals 0.08, sorry, 0.0818. So P hat, sorry, P is 90. Alright, we assume the P is 90, so this is 90 minus this. I'm gonna round it to, because this 1/8 won't make a difference. Sorry, so 0.9 plus 0.08. Sorry guys, I'm getting a little tired, so I'm starting to make mistakes. So this is 0.82, and this is 0.98, right? And this is this kind of flat C means it belongs to 0.1. So this notation just means that this is smaller than this. It's similar to this, but rather than saying a sharp thing with numbers, it's saying that this set is within this one. This one is smaller than this. Alright, so this is good. So now we can get to C. So first thing we did the proportion, which is the difficult part. Then we calculated if it's matching the need to be approximately 1. And then And then we need to find C. Assuming the retarded claim is true, find the probability that a sample of 121 would produce a sample proportion so low as was observed in the sample. Would produce a sample proportion so low as would produce a sample. So what we are asking is the probability that some sample proportion that we're going to find would be as low as ours. Right, so question is, if we take a sample from this population, will we get below what we measured? If we get below, it means that there's less people getting shipped than 102 out of 121. So this is kind of the setup. This is the breaking point, and this is what we're looking for. All right, well, yeah, right, well, then this. Let's look at it. All right, well, Z equals P hat minus mu P hat divided by sigma P hat. So in our case, that's 0.843 minus, this is right here, right? Because mu P hat equals to P. So this is 0.9 divided by this, right? So this is 0.0273. So that equals to 0.843 minus 0.9 divided by 0.0273. I got negative 2.09. All right, well, that's 0, negative 2.09, and we want numbers that are smaller. So this. So we look up our table, negative 2.09. It's 0.0183. So the probability for P hat smaller than 0.843 is 0.0183. So 1.8%. All right. So I just solved this, and first question that I'm going to get is, teach, oh my God, the page 107 in the textbook says that the answer is 0.0139 and your C-squared is wrong and whatnot. Well, to which I say, question where you round. And because we did rounding the way I did rounding, we got a slightly different answer. Is it wrong? No. I mean, we can do, if we did the calculation according to what the numbers were used in the book, divided by 0.027277, right? If you use the numbers in the text is using, you get negative 2.2, which is what they're getting, and it all makes sense. But because I used extra approximations, right? I rounded this, I rounded that. If I turn this into 272727, I'm getting this. Now, is this wrong? No, it's based on the approximations and the roundings I did. And so this is the very tricky part about doing numbers, is question when you round. If I kept my P hat extended for 15 decimal places, and I would keep this in 15 decimal places, I would probably get a very different answer. But because I rounded here and rounded here, I got this. Now the textbook rounds this into 8.4 and doesn't round this. It keeps it at 0.027272727 repeating, right? So they round one, they don't round the other. You have to make a choice. And again, if you're looking at your classmates' work and they get slightly different answers than you, or slightly different answers than the answer key, questions did they do the math right? Just plug in the calculator, see if the numbers match up, or if they just took them out of thin air. But the idea is that because I rounded, I get slightly different answer. And again, 1.8% versus 1.4%, slightly different, right? But this is what I got. This is how I did it. This is me doing it without looking at the answer key. So your answers will be different if you follow a certain things. Now again, it's better to have more decimal places than not. I choose to have, as you see, extra decimal places in most things. I just have extra places. Why? Because I just try to round the last step. And again, I should have maybe hold 3 or 4 decimal places in each one, and the answer would be different. But this is what I did. And again, this is kind of a conversation to be had. So if you're grading other people and they're getting numbers slightly different, and it says, hey, this is why your answer is different than the answer key because you rounded here, just give them my feedback and try not to be too harsh, because for me the important part is somebody went through the notions and checked everything and drew their picture and actually checked the tables, and all of it makes sense. The downside is they rounded here and they rounded here versus not rounding or rounding otherwise. So just a heads up. I hope you're still awake by the time this shows up. All right. So let's see. Let's look at D. Based on answer on part C, draw a conclusion about retailer claim. All right. How do we deal with this? The retailer, can we recycle some of this paper? Maybe this one. Right, I'm going to do it on recycled paper because it's going to be lots of drawings. So I apologize for the background. Don't worry about it. So the retailer saying that, hey, that's my distribution of times, and I'm very convinced 90 is right in the middle, right? 90% of the time I'm doing it within 12 hours. Like this is my distribution. There's some slower, some faster, but the average is right here in the freaking middle. So this is the distributor. Right? The distributor says this. What we did is we said, hey, there's something here at 0.43. This, right? We said, hey, we're looking at this kind of probability. And my question is this overlapping enough with this? Right? Is there enough overlap that this could have been a sample of this? Right? Or is it reasonable to assume that this whole thing is just loosely based on it, right? And so here's the thing. It's saying that how likely is that this is the population versus this? This is the claim, this is the sample that we try to do. Well, this sample, in our case, happened 1.83% of the time. 1.38% of the time is very unlikely, right? If this is very unlikely, then I don't have enough to show that this is wrong. Right? So this is this idea. If remember when we had this kind of distribution. Actually, let's make it a little bigger for the benefit. Alright, so this is the distribution we had, right? This is the normal distribution we had. And what we're asking is that if we have say this right here, right? How likely is that actually though you can barely see those. Let's how's that? Right. Cool. How likely is this that this is actually a major influence? Like we're saying the sample ends up here. Was it a very good sample? Or how likely is it that this is actually belonging to this? It's very, very small, right? If it's very, very small, then what we are saying is that this probability of this happening isn't very likely, right? The idea is that if the probability of something happening is very, very small, right, then it's very, very unlikely that the assumptions we made about this are true, right? We made the assumption that the distributor is screwing things up and shipping things late, or right? Well, is it likely that they do it? Well, no. We showed that it only happens 1.83% of the time, which means that most of the time he's shipping things faster, right? Because our calculation we're looking for. Oh God, I lost the page. Oh, here it is. Okay. Saved. Our calculation was here. That this is our assumption. That he is slower than 84% of the time. So he's somewhere here. This is the distribution we're looking for, right? This is the assumption. So if the probability of the assumption to be true is very, very low, and in our case again this is 1.83%, right? This assumption that is going to end up over here, then this assumption is probably wrong. If this is probably wrong, then we cannot say this is wrong, right? We could assert that it's probably right, but we cannot assume that this is wrong, right? Because it just happens so rarely, right? If out of all your grades you got one F in 4 years college career, it doesn't make you a bad student. No, it just makes you a student with an F, right? Well, because what if I take a random grade out of your grade book, and what are the chances of getting an F, right? Or getting an average of an F? Right? I take 5 grades. What are the chances I'm going to get an average of 5 Fs? Well, you got an exam here, an F. You got a homework here, an F. You forgot to show up here for an F. A couple Fs. Doesn't make you a bad student, right? So this is this kind of conclusion of like, hey, this is over here, right? If this whole thing was red, like a big chunk of it was red, then yeah, something is screwy, right? If this number was 18%, yeah, it happens way too often. Too often this is showing up. We are too curious about. But if it happens, 1.8% of the time, oh yeah, it does happen. Statistics no longer past chapter 3. Statistics is no longer about certainty. What we are talking about is how likely things are. Is this making sense? Is this compatible? Right? Are we building probabilities there? And we have to give ourselves some reasonable level of when things are unlikely and when things are likely. And things are unlikely when they're below 5%. Usually we talk about 5%, right? So 1.8% is just a very small probability. So the conclusion is that our assumption about this is wrong. Now, is this making the distributor right? No, but based on this sample, we don't have enough evidence to show that this guy is really screwing, right? Right. So we don't have any reasonable suspicion that his assumption that 90% of the time we get it on time is wrong. It's just, this is not good enough. Yeah, if this was overlapping like this, then we have some data saying, hey, this is happening too much. And again, we assume that the sample is random and fits, and then the distribution is not. There's a bunch of assumptions done, but overall, based on the information we have, the unlikeliness that he's screwing up is so small. We weigh it against just taking a weird sample. And 1.8% is just, if 1 out of 50 times you screw up, does it make you a screw up? Well, no. Does it prove you're not a screw up? No, but it's. I wouldn't go to court with 1.8% chance of something. Just wouldn't. Alright, so this kind of concludes chapter 6. The homework for chapter 6 is due on the 5th, is accepted till the 6th, so you guys have, right, 5th? Hang on, I'll double check that before I tell you a lie. Let's see, Laulima, class assignments. Yeah, it is due to the 5th, so it's accepted till the 6th, so we're good to go on that. And then the homework 7th is due on the 9th, so I'll probably be posting 7th soon. And then 8th I'm gonna hopefully post a video for 8th as well, so you can fight with that as well, but we'll see. If you have any questions, just keep posting them. I know there's a couple of you very active and a couple of you are very silent. It would be awesome if I could hear something from people that haven't posted anything recently. Just tell me something, and this way we can at least communicate, because I would like to know you are still alive and you're still with me, because otherwise, if you're not there, I'm talking to myself, and that's just crazy bones, and I'm not crazy. I'm just married. Alright, and on that note, guys, have a great day, and let me know if you have any questions. Bye.